Moments of inertia, type 3, rolling disc. So this question is taken from our row and tree handout, and we're going to do question 51 as our example. So we have a rough plane, so there's going to be friction involved, is inclined at an angle of alpha, where alpha is equal to tan inverse of 3 over 4, and the angle is with respect to the horizontal. And we have a disc of mass m, and radius r rolls down the plane, and it's rolling without slipping. So that means it's going to have both linear and angular velocity. And we have to find the acceleration of the disc in terms of g. And then the second thing we have to do is, if the disc is on the point of slipping, so coefficient of friction is going to come into play here, we have to find the limiting friction, I should say, is coming into play here, and then we have to calculate the coefficient of friction between the disc and the plane. So again, remembering to look at page 53 here, we're looking at a disc, so we'll have to get the moment of inertia of our disc, and it'll be through the axis of the centre, which is perpendicular to the disc, so half mr squared. And then obviously we're going to have to look at our potential and conservation of energy, and again, we know our kinetic energy from physics is a half mv squared. So just to remind ourselves of our rotating bodies here, that we have rotational kinetic energy is a half I omega squared. So let's write down our moment of inertia first of all. So I for the disk is a half mr squared, and the mass is m, and the radius we're told is r. So therefore, we don't actually have to make any change to the formula here. It is just going to be a half mr squared for the disk. Second thing we need to work out is our height for our principle of conservation of energy. We're going to need our potential energy, which is mgh, and therefore we need to know what is height. So the height above the horizontal, if it travels a distance of s down the plane, then we can say that if alpha is equal to tan inverse of 3 over 4, that means that tan alpha equals 3 over 4. And if we draw our right angle triangle, we have opposite, adjacent, and it's our favourite Pythagorean triple. So we can then write down 5 as our hypotenuse, and therefore sine alpha is the opposite, which is 3 over the hypotenuse, which is 5. So therefore I can say that h is equal to s sine alpha. In other words, h is going to be equal to s times 3 over 5. So in terms of s, we'll have 3s over 5. So whatever the distance travelling, our height above the ground will always be represented by 3s over 5. Okay, so let's look at our principle of conservation of energy. So we'll have our potential energy must be equal to, so our change in potential energy will equal to our change in kinetic energy, where our potential energy is beforehand, and then afterwards it's moving, so it's going to have kinetic energy. As it's moving down, it'll have both linear kinetic energy and also rotational kinetic energy. So our mass of the disk is m times g, and height we said there was 3s over 5, and that's going to equal a half m v squared plus a half an I. Our moment of inertia we said was a half mr squared times omega squared, our angular velocity. Now the question wants us to find the acceleration, which means we're going to look at the linear velocity. So we know therefore that the linear velocity's relationship with the angular velocity is that v is equal to r omega. So therefore I can say that omega must be equal to v over r. So I can actually rewrite that equation then as 3mgs all over 5 is equal to a half mv squared plus a quarter r squared. And instead of omega squared, I'm going to put in v over r. Then we have to square that. So that gives me 3mgs all over 5 is equal to a half mv squared plus a quarter m. And then we have r squared over r squared, which is going to cancel. So it'll be times mv squared. Now, of course, we have m, and m. And if I multiply across then and simplify, we have 3s over 5 is equal to a half v squared plus a quarter v squared. And that's 3/4 v squared. So then I can multiply across by 4, divide across by 3. Obviously 3 goes into 3 once. And therefore I can see that v, the linear velocity in terms of g, will be 4... Where's my g gone? Sorry, that should be 3g. So we end up with 4gs over 5. So the square root of 4gs over 5 is our linear velocity. Okay, so to find the acceleration, therefore, what we can say is v squared is equal to u squared plus 2as. We know that it starts with an initial velocity of 0 because it's starting from rest. We've just worked out the linear velocity there is the square root of 4gs all over 5. I have to be careful to make sure our s's and our 5's don't end up looking the same. And therefore, if I sub in, I get the square of 4gs over 5 square root is equal to 0 squared plus 2as. So we have 4gs over 5 is equal to 2as. So you can see that regardless of the distance travelled, the s is going to cancel there. And therefore I end up with my acceleration is 2g over 5. So our acceleration in terms of g is what we were asked for. So the second thing that it wants us to do is if the disk is on the point of slipping, so let me mark that, find acceleration, we'll call part 1. And then finding the coefficient of friction, we'll call part 2. So let's draw our diagram. So if we mark in our forces, we know that it's a rough plane. So if it rolls down the hill, we're going to have friction in the opposite direction. So we have linear velocity in that direction. We then have contact point, so therefore we're going to have normal reaction. Weight, obviously, is going to act in a downward direction. So therefore, if I resolve my weight into my parallel and perpendicular components, well, this angle here must be alpha. So therefore we end up with mg sine alpha, the opposite, and mg cos alpha, the adjacent. So again, always making sure you're using either a different colour when resolving or a broken dotted line like I have done here for the original vector. So therefore, if we look at parallel to the plane, because it's rolling down the plane, and we look at our net forces in that direction, then the leading force is going to be our weight minus the opposing force, which will be friction. That will equal to our mass times acceleration. So the weight parallel to the plane is mg sine alpha minus our friction is equal to our mass times acceleration. So the mass we know is just mg sine alpha. Well, we go back to the very start there. We said sine alpha was 3 over 5. Minus f is equal to the mass times the acceleration. And again, we've worked out our acceleration is 2g over 5 from part 1. So that means that F is equal to 3mg over 5 minus 2mg over 5. So it's just mg over 5. But of course, we know that F is equal to mu times R. So what that means then is that mu must be equal to F, which is mg over 5, divided by my reaction force. And if we look at the diagram there, we can see that the reaction force is equal to the weight in the downward direction, which is mg cos alpha. And cos alpha, if we go back to the start, we can see must be the adjacent over the hypotenuse, which is 4 over 5. So then we end up with 4mg over 5 for R. So subbing in then for R, we can see we have a fraction, so we're going to turn it upside down and multiply. So we have mg over 5 multiplied by 5 over 4mg. 5 cancels, mg cancels, and we're left with our coefficient of friction is 1/4. So now what you're going to do is on the sheet, question 50, question 52, and question 8, which is basically marked as the 2008B question.